Now, what we are going to be discussing today is an area of mathematics called graph theory, which is not at all in any syllabi in the UK, definitely not A-level. It is a bit in if you're doing IB, so that it is in IB, but generally it's definitely not school syllabus. So if you find it a bit tricky, don't worry. But I think some proofs, other than some proofs, most of it will be accessible for everybody. And I hope the proofs will make sense as well. We have quite a lot of people saying three people, 11 people saying three colors are enough, 51 people saying four colors, 23, 29, and 21 people going for 5, 6, and 7 colors. So by far 50 is the most popular, but we still have altogether quite like more people, sorry, 4 is the most popular, but quite a few people opt for others. Now, actually, when this person called Francis Guthrie wanted to colour the map of England, he realised that actually he can do it with 4 colours, but he couldn't do it with less than 4 colours. So actually there is a reason why you need 4 colours. Why 3 is definitely not enough, and I'm going to show that to you. So if you have, I'm going to circle the area which is responsible for that. It's going to be this area there. Because let's say I pick any color, let's say I'm going to pick blue for that middle bit, then this area next to it must be of a different color because it's next to blue, so it must be not blue. I picked orange. And then if you're picking like this one, it again must be a different color because it can't be orange and it can't be blue, so it must be green. And then if you're picking, like looking at this area, it's actually a neighbor of all 3 of the previous colors, so it can't be orange, blue, or green. So we need to have a 4th color. So it's actually, in this case, if you spot that middle of the map, you can see that 4 colors you most definitely need. It's not at all obvious how to color it with 4 colors, to be honest, and I tried to color it myself yesterday, but then I sort of gave up at this stage, and yeah, it is not obvious at all how to do it. But this guy did it, and he was wondering, well, is it possible for every map to use 4 colors, or sometimes do we need 5 colors or 6 colors, or how many colors do we need so that we can be certain that color a map? And actually, I'm going to ask you to do a bit of coloring. Obviously, it's going to be a bit harder for you on these ones because you can't, if you can color on the screen, that's brilliant. Otherwise, just try to visualize it. I'm going to give you about 3-5 minutes just to look at which one is the hardest, like which one requires the most colors and what is that number of colors. So is there any you need 4, 5, 6? I'm going to do another poll and you can think what is the maximum number of colors you need for one of these. Okay? Okay, so I'm going to show the responses now. We have quite a much more even distribution of answers. So still most people think that 4 is enough for these ones, but quite a lot of people went for 5 and 6. I'm just going to do 1 because I think doing them will also help us later on with some proofs we are doing. And I try to color all of them myself. So I'm going to pick the one which I struggle the most with, which is this one here in the bottom, this one. So what I do usually is the same as with the maps. So I start with 1 And then I color the neighbors different colors. So if that's yellow, then next to it must be orange. And then, for example, I know that below it, this funny shape must be a different color to blue, yellow and orange because it's a neighbor to both of them. But now I want to use as few colors as I can. So I want to reuse yellow for this one because I can do that yellow. And actually that one in the middle is quite doable with an orange, right? Because it only has those two neighbors. Now moving on, I can use the orange for this one as well. So I'm trying to use always what I have. I didn't need to introduce a fourth color just yet. Now I must have this one as blue, don't I? Because it has orange and yellow next to it. And then below it, this one is actually has to be yellow. Then because of that, this has to be orange, or obviously a different color, but again, I don't want to introduce a new color yet. Then what do I have? I have on the other side, we need to have a blue. And then this one, again, it can be blue because it touches an orange and it touches a yellow, but it can definitely be blue. And the tiny one on the middle, I could color that yellow, but then this one need to be orange. And if I want to do the same coloring, this one could be yellow because yellow is a good color to use for that one. But then if you look at this big area on the left, it has a yellow, an orange, and a blue neighbor. Also, if you look at this area in the bottom, has a yellow, an orange, and a blue neighbor. So if I do this coloring, I would actually need a different color for them. Now, it turns out it's just me being clumsy or me not finding the best coloring straight away. Because actually it's possible to color it with 4 colors, but just going ahead and always picking a next color, sometimes it's called a greedy algorithm. It's not always useful. So now I could only manage it with 5. Turns out that you can do it with 4. So in the next slide, I have everything actually colored with 4. It takes a bit of thinking how to do it. And that's what we are going to do today. Just like look for efficient ways to color, but more like prove how many colors we actually will end up to need. So actually, I think out of these, one of them, that one, which looks hard, that only needed 3. Everything else needed 4, but 4 was enough for everything else. Now, I want to give you another task again, which is, can you try to design a small map? It doesn't have to be a map that requires 5 colors. So we haven't seen one that needs 5 colors. And I suppose some of you are thinking, oh, is it too hard? Does it need to be like a super big map? We will figure it out, but have a go. It will also help you realize or understand the proofs later. Now I have this email address here, and the bottom enrichment@ukmt.org.uk. I'm going to give you about 5 minutes. Try to find one which requires 5 or more colors, and just take a picture, or if you do it in Paint, just send it in Paint, and hopefully if you receive one, I can show them to you. Okay, well, thank you very much. So we've received a couple of entries, and they look really creative. Now, I have to admit, I tried to draw one of them, but I'm too clumsy drawing on the screen. I will actually take the time and just answer how the coloring could be changed on some of them, because unfortunately none of them works, which is in fact, to be honest, one of them works, and they deserve an absolute honorable mention. It is for Henry, who did it on a torus. I might explain it at the end, but I love it. Brilliant idea. But actually, the reason why nobody could do it is because it is not possible. There is a theorem, a lot of you also mentioned it in the emails, the 4-color theorem, which actually says that every map can be colored with 4 colors. Now, we won't prove the 4-color theorem today, but we will prove the 6-color theorem and then the 5-color theorem, and have a go at like thinking about how we can prove something like this. Now, basically, when we have these maps and colorings, that's actually super hard to talk about them. Like maps look a bit weird. Like if I look at this map, for example, like I can say the oval shape bit in the middle. It's not very easy to speak about them. Obviously, we could label them or number them, but what we are actually interested in, we could maybe look at the capital of every country. So if these are countries or these are counties, do counties have a capital? Well, the center, we can look at the center of each of these regions, and basically we can imagine just giving a color to these points. And actually, what we can also do is connect the neighbors. So if a country or if a region is a neighbor to another region, we just connect the 2 points. I will try to do it here. So, oh, that region didn't have a point in it. So if you do that, then actually you will get a quite simple structure. Now, I'm not going to do all of them, but I have a picture where I've already done it. I don't want you to wait ages of me connecting them. There are advantages, a lot of advantages of connecting them like this. One thing is we can actually label them, speak about them quite easily. And we can also move the points around a bit. So actually we can realize that 2 maps, which look somewhat different, are in fact the same map. Let me show you an example. If we have this map, then the corresponding little representation would look like this. So actually, we would just have this. Now that could look somewhat like that. It could be like that, and then it could look like, I don't know, that and that. That would actually be the exact same situation. Now this way, we simplify the situation. We can represent multiple situations with the same diagram, so we save a bit of time. Did I do that? No, sorry, I don't need that. That's not a point, that's a point. Now actually, this is what's called a graph. A graph, you might have all met the graphs which look like that. It's spelled the same, but it's a completely different concept. In a graph, we have points, which are called vertices. So this is a vertex. We have edges, which connect to a vertex. And actually, that's a graph. A graph is the connection of edges and vertices. Some vertices are connected, some vertices are not. And if 2 vertices are connected, they are called neighbors. Now, this graph is actually something special, because what you can do with this graph is you can draw it on a piece of paper without the edges crossing, which will be really important later on. It's called a planar graph. It's going to be written in the next page. Actually, why planar graphs are super useful in this case, because if you just imagine a map of any country or any region or any of these maps we've dealt with, if you pick a center and connect the neighboring countries up, you could always draw it as a planar graph. You can always draw it without the edges cutting each other, because basically from every vertex, every center of country, you just go to the border with the neighbor, and then from the border, you go to the neighbor. So it's quite easy to see that if you have a map, you draw a graph, it's going to be a planar graph. And we changed the problem, we rewritten the problem to saying we have a planar graph, we want to color the vertices such that no two vertices that are connected with an edge are of the same color, which is going to be super useful later on. Now, we are going to be speaking about connected planar graphs, and if I just say a theorem and I'm not saying connected planar graph, I should, but just bear in mind that we are dealing with connected planar graph. Now, connected means if I have a graph here, like so, it wouldn't have like a standalone vertex that is not connected by an edge to the rest. In a map, that would also be quite odd, although it could be, for example, an island. But we are not dealing with those. We're only dealing with connected graphs. But obviously, if we have like a separate bit or even like a separate component, if we can actually color one of them, then we can color the whole thing. Okay? Now, I'm going to connect this because I want to have connected graphs, and I'm going to draw a couple of examples. Not too many. Maybe this one, and maybe like a very simple one like so. Okay, so let's label them 1, 2, 3. And actually, we are going to prove a couple of facts, theorems about just planar graphs. Now, what we can do, we can actually count some things on these graphs. First of all, we can count the number of vertices. We can also count the number of edges, and we can also count the number of faces, which is basically tells us how many regions does this graph cut the plane into. So, for example, if you are looking at this first graph, it's really easy to say we have 1, 2, 3, 4, 5, 6 vertex. We have 1, 2, 3, 4, 5, 6, 7 edges. And if you want to have the faces, we would have this face, that face, and like a large face all around. So it cuts the plane into 3 regions. Now, if you look at the second graph, it has 1, 2, 3, 4 vertices, 1, 2, 3, 4, 5 edges, and 1, 2, 3 faces. And the third one is quite a simple one. It has 3 vertices, 2 edges, and actually it's just one face, the whole plane. It cut a hole into the plane, but it didn't cut the plane up into actual pieces. Now, if you look at this, you might be able to observe a connection, which is actually the following. If we add the vertices and the faces, we would get 2 more than the number of edges. So 6 plus 3, 9 is 7 plus 2. 4 plus 3, 7 is 5 plus 2. 3 plus 1 is 4, which is 2 plus 2. Now, mathematics, obviously, it's not enough to say, okay, it worked for 3 examples. We want to actually really, really prove it for everything. And it's not actually that hard. We will be using something called induction. Now, some of you might have math induction, and some of you haven't math induction, but actually it's quite easy. What I'm going to say is I'm going to say that this is true. Let's look at the number of edges of a graph. Now, if a graph has 0 edges, then this is the only possibility, like a single point. It has 1 vertex, 1 face, the edges is 0, so actually 1 plus 1 equals 0 plus 2, so that's good. Now, if you have a graph with 1 edge, this is the only option with 1 edge. And here we have 2 vertex, 1 face, with equal to 1 edge plus 2. So it's true for 1, it's true for 0 edges, it's true for 1 edge. What we want to show is it's true for every number of edges. And with induction, basically what we are doing, we are saying that, say if it's true for k number of edges, if k edges, it's always true, then k plus 1 is also true. So we are supposing it is true for k edges and proving it for k plus 1. Now, let's suppose Suppose, so we get vertices plus faces equals edges plus 2. True for the number of edges up until k. Now, if we have a graph with k plus 1 edges, we can have one of two things. One is, if we have a vertex that only has one edge, that only has one neighbor, then we can separate that vertex off, and then here we have a graph. And why that's good is because the part of the graph that I've circled, that part of the graph only has k edges. And we know that our equation is going to be true for that one. So basically, what we want to show that if it's true for the one inside the circle, it's true for the whole graph. And it is, because when we are adding that extra bit, this one, what we do, we add one edge, so we add one to the right-hand side, but we also add one vertex to that side. So actually, the equation stays the same. We don't have any new faces or anything like that, so it's quite good. Now, this doesn't always happen. So sometimes it's going to be the case that every vertex has at least two neighbors. But actually, if every vertex has at least two neighbors, and here I'm not going to be 100% thorough, but basically, imagine what happens if we have a vertex and everything has at least two neighbors. Then if we just always just go for the next neighbor, after time, we are going to arrive to a point where we've already been. It might not be where we started from, but after time, we are going to arrive and get something called a cycle. Now, why this is actually quite good is because now I'm going to say that if I have one of those, I'm going to remove this edge. Now, if I remove that edge, I have again k edges. So without that edge, my equation is true. If I add on that edge, let's see what changes. We actually, if we add back this edge, we get one more face, because that cycle there just cuts off one face. So actually we would have +1 on the faces front, and we would also get +1 on the edges front. But we wouldn't get new vertices because we just added back that edge. So actually the equation stays true, which is going to be super important. So this is true for all planar, connected planar graphs. Now, from this, you will need to do some thinking and some algebra. I'm going to give you just a couple of minutes to think about it. We want to prove that for graphs, so for graphs with at least 3 vertices, so V is at least 3, we want to show, first of all, that 3f is going to be less than or equal to 2e. Okay? And we also want to show that 6 is less than or equal to 3v minus e. These two things you can actually think about. I'm going to give you just really 2 minutes to think it through, and then we are going to be discussing it. Okay, so I appreciate this was far from enough time for anybody to really solve this if you haven't seen it, but hopefully you had like a minute to think about it. Actually, when we want to bound the number of faces, let's just look at how a face looks like. So a face would look like we have vertices, they are connected, and then that's a face. So we have the inside faces, which are basically inside polygons. Actually, they are inside polygons. And the other thing we might have is the outside face. So for example, if we have this, we have this outside face all around. So we have inside faces and outside faces. And for inside faces, it's quite easy to see that every face will have at least 3 edges surrounding it. So for every face, there belongs 3 edges around it, because a polygon couldn't have obviously less than 3 sides. Now one might be thinking, could I have something like this when we have 2 points connected with 2 edges? But that doesn't make sense, because if you look at two neighbors, that's like connecting 2 neighboring countries twice. That's illegal. So we don't need to worry about that. Now, the other thing we might need to worry about is the outside faces, how many edges the outside faces see. And actually, the outside faces will also see at least 3 edges, because they see, like, the simplest case would be this, which some people have been thinking, and they're saying, oh no, that's not 3. I can definitely say that's true. And you're actually right. That simplest case looks like it's 2, but actually if you're just like an ant or something going around and being a bit silly, you would be thinking, okay, that's one face, this is another face, that's another face, that's another face. So you would have 4 faces. And if you have something more complex, then you would have even more on the outside. Actually, it is not cheating. In a way, it is cheating. But even if you look at the 3 faces belonging to every inside face, every polygon, 3 edges belonging to every polygon, every edge is actually seen by 2 different polygons. So actually what we can see is the number of faces needs to be at most the number of edges divided by 3, because for each edge there's only going to belong, each face there belongs 3 edges, but we need to multiply the number of edges by 2, because every edge actually is next to 2 faces. So we can see that F is at most 2e over 3, or if you want to multiply up, 3f is less than or equal to 2e. So this is only true for connected planar graphs. Now, the second equation after this is relatively simple. You want to use your original equation, so we have v plus f equals e plus 2. And I will want to, if you compare, so now I'm going to circle our goal, our second equation we want to find. If you look at that, we don't have faces in that inequality. So what we want is just to substitute in edges instead of faces. So I think it's quite a bit easier to do if I just have faces on one side, so that would equal to edges minus vertices plus 2. And because our inequality is for 3 faces, I think it's just nice if you multiply it up by 3, because then I don't have to deal with fractions, which is always a bonus. So 3 faces equals 3 edges minus 3 vertices plus 6. And now we know that 3 faces is less than or equals to 2 edges, so I can just write 2 edges there. Now if you rearrange, you just get 6 is less than or equal to 3v minus e, because you just minus 3e from both sides, and then you get 3v. I would correct that equation because it looks really ugly, but if I delete something, then every writing disappears in this program, so it's going to stay like that. Now, why this equation is quite nice, and I think we need to stop for a second to appreciate that, is that, or inequality, it doesn't have faces in it. And generally, if you have a graph, counting edges and vertices is much easier, because basically that's the definition of a graph. You can store a graph multiple different ways, so you just know how many vertices you have and who's neighboring who. So you don't need to have like a drawing of it. That's why this inequality without faces is quite useful, and that's what we are going to use quite a lot later on. And now we arrive at this 6-color theorem, and we're actually almost there. What we are going to do, we are going to do 2 different methods of proof. We are going to do induction, and then later on we are going to do a contradiction within that induction. So induction is basically, again, we are going to say, well, if I should have stated what the 6-color theorem is. We want to prove that every graph, every connected planar graph, you can color the vertices with at most 6 colors, such that no 2 no two vertices have the same color. Now, it is quite easy to prove for v less than or equal to 6, right? If you have at most 6 vertices, then obviously you can color them with at most 6 colors. It would be quite hard not to be able to do that. You can't even use more than 6 colors. So what we want to prove then with induction, we say if it's possible, so we suppose we can color for the number of vertices less than or equal to k for some number. And we want to say, okay, what do we do if the number of vertices is k plus 1? If I have the graph k plus 1, I want to be thinking, I want to reduce it. I want to take away one vertex such that the remaining graph I already know how to color. And then I just put that one vertex back and I just color it appropriately. And one way it is super easy to be colored is if that vertex only has 5 neighbors. Because if there is a vertex which only has 5 neighbors, then I pick that vertex out, color the rest of the graph. Then the neighbors could have at most 5 different colors because it only has 5 neighbors. So when I put it back, I just color it the last color and I'm done. So actually, what we will want to prove is there is a vertex with at most 5 neighbors. And we are going to use our previously found inequalities to prove that. So generally, if you want to prove that there is something, quite often the easiest way to prove it is say, okay, what happens if there isn't? Which is called proof by contradiction. So I'm going to say if all vertices have at least 6 edges. If all vertices have at least 6 edges, then the number of edges will be 6 times the vertices. No, actually, I'm not being serious. It's not going to be 6 times the vertices. It's going to be very similar to that. But you need to remember every edge belongs to 2 vertex. So just because every vertex is going to be have 6 edges around it, because every edge belongs to 2 vertex, actually the number of edges will be at least, that was a really ugly at least 6v over 2, so 3v. Now, if we have that the number of edges is at least 3v, then we have that 3v minus e is less than 0. I think you can see why that's a contradiction, because we've just proved that 3v minus e is at least 6. So this is not possible. This is a contradiction. Now, what will that mean? It's going to mean that there's going to be at least one vertex with 5 neighbors, because not all of them can have at least 6. And then we can finish our induction and say we can always just pick from a graph on k plus 1 vertices, one vertex which has at most 5 neighbors. We can color the rest, we can put that vertex back, and then we prove for k plus 1, which finishes the induction. 5-color theorem is going to be actually very similar, but it's a bit harder. Now, the problem is, if you try to use the same sort of idea for the 5-color theorem, what you really want to prove is that actually there is in every graph one vertex with 4 neighbors. Because for 5 colors, you need a vertex with 4 neighbors to be able to do the same thing, which you can't prove because it's not true. But actually, if you do a very similar calculation, what we've just done, you can find that it is true with graphs of at most a certain number of vertices. So you can use the same theorem to prove that the 5-color theorem is true for the number of edges less than or equal to a certain number. And actually, I want you to try it yourself. So I'm going to do a small poll. It's quite like it is not easy, but it's not also not super hard. So if you understood the proof, I think you can do it. I'm going to give you 5 minutes, find that, and I'm going to give you some options in a poll right now. Okay. Again, I'm really sorry. I didn't give you far enough time for this one. So you would need absolutely more time for this. But actually, I'm quite happy to see. Let me show the responses. That the correct response is the most popular, which is generally a good sign. I'm just going to quickly show why that response is actually correct. So why this would work for 30. Let me open a new page. So using the same argument that we used, if we want to prove that there is one vertex with at most 4 neighbors, we want to prove that it's too much to have 5 for everything. So if all vertices have at least 5 neighbors, then we would have the number of vertices would be, sorry, the number of edges would be at least 5e divided by 2. And again, that's because an edge belongs to, sorry, 5v belongs to 2 vertices. So 5v divided by 2. Now we have this equation, which we definitely must satisfy, is that 6 is less than or equal to 3v minus e, right? So we want to sub one of these back into it, and I want to express v in terms of e. So actually you have 2/5 of e needs to be more than v. And if I sub it back there, then 3v is going to be less than or equal to 3 times 2 over 5e. So this is going to be less than or equal to 6 over 5e minus e. But then we just got that 6 is less than or equal to a fifth e, which we got is that e needs to be at least 30. Now, what it means that if e is less than 30, this proves that if e is less than 30, this proves that that graph can definitely be colored with 5 colors. Now, the fact is, 5-color theorem and indeed the 4-color theorem works for all the planar graphs, connected planar graphs. We are not going to prove the 5-color theorem today, but we are having another talk next week on Thursday, when we are going to look at the 5-color theorem, and we are also going to look at the 4-color theorem, although we are not going to prove it. Now, what I have here, and actually some part of the presentation, are also from a book from Jerry Laversha and Dominic Rowland, which is published in the excellent UKMT handbook series. And this book is called Topics in Combinatorics, which is my favorite book from the whole series. it has a lot of interesting combinatorial things. So I really recommend you have a look at it if you want to have some summer reading. But also I have a couple of questions here. Now this presentation will go to YouTube, so you can see it there, or maybe you can have some time to quickly screenshot the questions if you want to think about them, because they are quite interesting. And now you know everything to be able to solve this, although you will need to do some thinking. If you write them down and drop us a message at the email address there, enrichment@ukmt.org.uk. I will have a look and will tell you whether your proof is correct or not, or help you with that. And hopefully I'm going to see some of you. Well, you're going to see me. I'm not really going to see you. Hopefully some of you will be here next Thursday to discuss the 5 color theorem for every cases, not just less than 30 edges. Thank you very much for listening.